you are interested in salinity tolerance, you will want to have some salt tolerant accession as well as salt susceptible. Don't focus only on one group, only on the resistance, because you may not see any difference. Okay? You will conclude by comparison. So you need to have, if possible, the extreme. You need to understand the genetic organization of the collection. And generally, to do that, you will characterize your collection with neutral markers. Either you do it yourself, or you use a collection established by someone who has already characterized the collection. So here is an example of collection of rice varieties. I don't know how familiar you are with rice, but in rice you have two subspecies, the Japonica and Indica, that are very clearly different. So here you have the Indica, and here you have the Japonica. And if you go a little bit further, you identify 4 different groups. So you have still your Indica, but there is a special group from Eastern India, which are called house and boro actually. And they are slightly different from the Indica. And you have also the aromatic accession, the Sandwich and Basmati, represented here in green, that are also slightly different. And why do I need to know all this? It's because it will be helpful after that to explain what I am looking at in terms of diversity. I may find that some SNP, some mutations are specific of the Indica group and not existing in the other group. And it's very helpful to have as much information as possible on your accession to be able to explain what you are going to get as data. Population size, how many accessions? Well, it depends on your objective. If you just want to test sets of primers to amplify pieces of the gene, then maybe 8 to 24 is enough. I mean, why I'm saying that is because a PCR plate has 96 wells, so you have sets of 8 accessions, so it makes sense to have multiple of 8, and 8 is already good representation of diversity. If I go back to my rice example, I can take 2 Indica, 2 house, 2 Sandwich Basmati, and 2 Japonica, and then something quite different, well representative of the diversity. Now, if you really want to go to establish a relationship between phenotype and the polymorphism you identify, then you know you need to have a larger population. And generally, population of 200, 300 accessions is needed. Okay, this is the, okay, there is no limit. If you can handle more, it's fine. But generally, the problem is to phenotype accession is difficult as soon as you have more than 100. Okay. On an evolutionary point of view, it's also interesting to add, if you have the resources for, a few wild accessions. The wild accession will allow you to see, to look probably further back, and to see what the ancestor could have been, the ancestor of your accession. But generally, you don't need to have many, a few would be enough. And the second point, if you have a choice, you need to have good passport data on your accession, good information on your accession. This is really essential. As I said, these elements are useful to explain your results. They can allow some quality control on the data you are getting. As I said, in rice you have this clear split between Indica and Japonica. And generally, when I look at a mutation, there is an Indica allele and Japonica allele. And when I see an Indica allele with a Japonica, an Indica accession with a Japonica allele, I have to think twice whether it's truly a Japonica allele into an Indica background, or whether it's a mistake at some point, a mixture or misscoring of an accession. What I wanted to stress is the fact that there is actually very little information, useful information in gene banks, and often not for all accessions. I thought that rice data bank was really a good one, but what I could find on the rice accession that were coming from Gene bank, I found the country, was no indication of the point of collection, no latitude, no longitude, no elevation. So, I mean, if you are dealing with a small country, it's fine. But when you are dealing with India, I mean, whether it comes from Tamil Nadu or from Bihar, it's not the same thing. Same thing for China. The south of China is tropical, the north is temperate. So it would be useful to have more information than just the country. Elevation, same thing. If you are interested in cold tolerance, you need to know whether the variety was collected at the sea level or at 1,500 meter elevation. Meanwhile, also hydrology is very important. Are we dealing with irrigated variety, one-tableland or upland variety? These are elements of adaptation, and if I want to look for drought tolerance, I will look more at upland adaptation than at irrigated ones. Also important element is whether the type is a traditional adaptation, a land race or not. If it has been, it's an improved variety, probably the genome has been reshuffled, so it's not exactly the same thing than land races. And in the case of rice, this was, we had good data on that, and we had also good characterization of the population with neutral marker. We had isozyme data, we had multi-satellite data, so this was fine. But the rice was missing. While this could be quite useful element to establish guidelines for phylogeography approaches. You want to make links between data on climate or soil in given areas and the haplotype or the mutations that are dominant in another area. Okay, so if you don't have information on where this accession comes from, you cannot do that. And now with these GIS databases, you can have for any point in the world information on the average temperature, average rainfall, and so on. And all this is important to characterize your accession. So I don't know if you happen to do collection presently. Now I suppose that people who collect accession, new accession, they go with a GPS system and the geo-reference the position where they do the collection. In the old days it was in papers, and people didn't transfer this into databases, and it's a pity. So to start to work, you need to have sequences already. You cannot start from scratch. So you need to collect existing sequences, and probably you, of course, will produce new ones. So how do you get to reference sequences? You need both nucleic and proteic generally. First, you will go to papers or to databases. More and more in databases, you have the whole genome sequences, both all DNA nucleotide sequences and protein sequences. You need to have manually curated annotation if possible, because most of the genome are annotated automatically. So the limits of the genes are not very clearly defined. The limits of exon and intron are sometimes wrong. So it's better to have manually corrected annotation. It's good to have DNA libraries as well, because they help you to annotate correctly the gene. And of course, the fact that these sequences are available, it's also an element of choice. If you don't have a starting sequence, there is nothing you can do. And the last point is, if you are not working with a genome that's completely sequenced, you need to go regularly to the databases to retrieve new sequences. It occurred to us with our work on sorghum. We did the orthology relationship between rice that was fully sequenced and sorghum at this time was not fully sequenced. So we identified, I don't remember exactly how many, let's say 8 ASR genes in sorghum. And 3 months later, there was an update in the data bank, and there was a 9th ASR sequence in sorghum. Okay, so you need to update them regularly. If you have only information from another species than the species you are interested in. You can produce sequences on your own species, but it's quite difficult. You need to use complex methods to design consensus primer and to use this consensus primer to amplify the gene in your species. So what we used to design this consensus primer were tools such as allele or Courtois, but globally we were not very successful in doing that. And I mean, if you are just starting, I would not advise to use this kind of tool. It works only with very closely related species. For example, it worked well between rice and sorghum, but as soon as we started to try to go further with chickpea, there is no possible, nothing possible. Well, I skip the new method. So you will have to produce new sequences, and if you have already the sequence of the gene of interest in your species, what you have is just to design specific primer for your gene. This is relatively simple. Tools such as Primer3 do it very efficiently, but the difficulty might be that your gene belongs to a large gene family. And in this case, if you want to amplify one gene and not all of them, you need to have a specific primer design. I think that some lecture will be devoted to that later on in the, during the training. Now, what are you going to sequence? A gene is composed of intron, exon, and the promoter zone. What are you going to sequence? All of this, part of this. Again, this depends on your objective and your funding. Of course, if you can sequence the whole gene, it's better. But as I said, gene size can vary from 500 base pair up to 15 kb. So the cost can vary from 1 to 30 times. So if you want to sequence the whole gene, you might be able to sequence only a few of them. While if you focus on a segment of the gene, you may be able to look at more. This would depend on your objective. Should you, if you don't go for the whole gene, what to choose between exon and intron? So exon are the coding sequences, coding part. So exon and exon frontier, all the splicing area, are the areas that include functional polymorphism, and because of that they are interesting. Intron, in the other hand, are generally much more polymorphic. So it's sometimes quite interesting to have polymorphism to test some hypotheses on the gene. And you can decide that you want to sequence all exons, but it's not as simple as to say it. Often, it's very difficult to sequence some zone of the gene. In rice, for example, the first exon is having extremely high GC content. So it's extremely difficult to do a PCR on this part of the gene and to sequence it. You need to go to specific technique to amplify this segment. Okay? A good idea when you have a very large gene and you are interested in functional aspect is to sequence the gene corresponding to the functional domain. You can have one or several functional domains in a protein that correspond to similar area in the gene. Tools such as InterpoScan can help you define what are these domains if you don't know this in advance. And you can choose to focus your sequencing on this area containing the functional domain. So this morning, Dr. Ramandan talked a little bit about promoter and how this was important for gene regulation and how it could be useful to look at promoter. So generally, when you speak about promoter, people say that it's more or less in an area of 1 kb upstream of the ATG. Yes, it's fine. It's often like that. But on maize, there was a very nice study done by Italian scientists who showed that a QTL called VGT1 that was affecting duration in maize. Was located 70 kb upstream of the transcription factor AP2. So the regulating element was a non-coding element 70 kb upstream. You are not going to sequence 70 kb just to look for that. Okay, this may be an exceptional case, but this is just to say that promoters are less well defined than genes, and it's often difficult to know where to stop. So if you want to sequence the whole gene, then you're better since you often sequence by a fragment, you better have an overlap, reasonable overlap between fragments, because the beginning and the end of the sequences are generally of poor quality. And people wonder whether there was a need to sequence in both directions the gene. Again, if you have a lot of money, you will do both directions. But when you look for, you go for allele mining, you are generally aligning hundreds of sequences together. You don't need to do forward and reverse. One direction is enough. So, to summarize, what to sequence? If you are interested in gene function, you will go for exon. So this is a gene with 2 exons and 1 intron, and a 5' upstream region and a 6' UTR. So gene function, you sequence the exon. You are more interested in gene regulation, you will go for the 5' upstream region, the intron, or the 6' UTR. And if you have lots of money, and you can go for the routine. It's not a bad idea, and some cases, if the gene is small, it's perfectly feasible. How to sequence? Oh, it's not my field of specialty, and you will have a talk on that, so I will not go very much into detail. Up to recently, everybody was using the Sanger method, which is the classical one, which gives high quality, relatively long fragment of, let's say, between 500 and 1,000 base pair, but the cost is high. You can sequence either a PCR product directly, or you may need to have to clone the product before sequencing. Again, I think you will have a talk on how to clone product. So there are second generation technology, new sequencing technology. Generally, what I can say is they are way cheaper than the Sanger method, but generally they produce smaller segments. And the major issue is error rate. They have generally a higher error rate. So when you want to deal with SNP, it's a little bit of a problem. This error rate, things are improving, but still Sanger, in some cases, is not such a bad choice. And third generation, people are speaking about Pacific Bioscience technology, nanopore, where you will be sequencing molecule by molecule. And for people dealing with heterozygote crops, this could be interesting because you will not have any more to determine the phase, which can be quite tricky. So, you have chosen all these, the genes, the panel to work with, you have done your sequencing work, and you get what? You get this kind of product, at least if you have done your sequencing through Sanger. So these are traces. Each trace represents a sequence of a different